No, how are you? I need to go back on this particular category. Some of you have found that some of this work was edited out. We're in gases, masses and moles for a moment again. We have everything else done, but some of you have not got the piece on video on the kinetic theory, and I better go back in it again. So let me go through it quickly with you again and make sure everybody's okay. Right? Basically, this is a theory which simplifies the properties and the behavior of gases. And you shouldn't really have any issues with it. I have it up there for you now. This theory explains many of the properties of gases and the gas laws. Now, we have 4 gas laws done already. I hope you're okay on them. And each of them in turn could be developed by you. Okay, Boyle's law is for a gas at constant temperature. Charles's law, a gas at constant pressure. Avogadro's law refers to gases under the same conditions of temperature and pressure. And finally, Gay-Lussac's law is about combining volumes of gases. Okay, now you have them already and we've covered them in detail. Look at the previous video if you're not sure of this, okay? But this section here, I've made reference here to Brownian motion. Brown, the scientist, observed that when smoke particles were in a sealed chamber, he could see the large lumps of soot or smoke bouncing around the place. And he concluded that the air or the gas inside in the same chamber must be behaving in the same way. So he concluded that gas particles are in constant random motion. And that's the bit you need, okay? Constant random motion. Now, I think we've all got that far. The bit that most of you have missed now is the next piece. So I must slow down a little bit and make sure you're okay with this, okay? The kinetic theory of gases is based on assumptions. Now, can I clarify that again for you? Assumptions have no scientific basis. Okay, we often come to, we assume something and we later prove it's wrong. And that's exactly how it is in science. Something is correct, a theory is correct, until somebody will prove it wrong. Okay, and some theories still hold to this day because nobody has come up with evidence contradicting it. And that's very important for you to be aware of that, okay? So you're dealing with the assumptions of kinetic theory here. There's a total of 5 of them. There's 10 or 12 of them in reality. But 5 of them you'll survive admirably for leaving cert with them. Number 1, the particles are in constant random motion. Constant random motion. Okay, in other words, they're always moving. Now, will you remember the model we have of a gas? If you take any sealed chamber like that, the gases are in there, the particles, and they're moving around the place in a random fashion. They're colliding with each other on the walls of the container. So they're in constant random motion. Now keep in mind, this is a simplification, and that's good because it allows you to understand it better. 2, there are no attractive forces between these molecules. They have no effect on each other according to this assumption. Okay, you will find in a moment that that's not quite true, but it's an assumption, and we'd like to think that they were totally independent of each other as they ran around. Okay, next, the gas molecules occupy no space. They're so small, the space they occupy is negligible. So we say they occupy no space, right? Number 3. Number 4, conclusion. The collisions are perfectly elastic. When these particles collide, they don't lose any energy. Now, that's a bit technical, and there's a bit of physics in it. I wouldn't worry too much about it. That's why I put it at the bottom half of your list, okay? Be aware of that. According to this theory, the collisions between the particles are perfectly elastic. And number 5, the kinetic energy of the molecules is directly related, directly proportional to the temperature, suggesting that if you double the temperature, you double the kinetic energy. That would be the implication. There's a direct proportionality between them. Now, they are assumptions. You are likely to be asked in leaving cert to state or to give 3 assumptions of the kinetic theory. And I would be advising you now to take them in the order in which I've given them to you, because you can defend them best. You're most equipped as a chemistry student to defend the early ones than the later ones. But I have given you 5 because you might find yourself in a position where they've given you 1 or 2 on the question and ask you for 2 more. So please make sure you have 5 of them. And if you have 5, you'll be able to answer any question you're asked. Now, the next thing I need to say to you then is we've already comprehensively covered the idea of gases. Real gases are gases that we produce in the lab, or gases that are in the air, or gases that we can use in a practical sense. Are you okay with that? And that's what we mean by real gases. Now, we must develop the concept now of an ideal gas, because it's very important in chemistry to have this concept. An ideal gas is the perfect gas. It would obey all the gas laws under all conditions of temperature and pressure. I'll define it for you in a moment, but first of all, just the whole idea of ideal. We all aspire to some ideal. We never reach it, but we aspire to it, and that's quite understandable. The real gases and the ideal gases we must understood. There are limitations to the assumptions of the kinetic theory if you're dealing with real gases. And that's what they're going to ask you now in your exam. First of all, to list some of the assumptions of the kinetic theory. And secondly, they are going to ask you, what limitations are there for these particular assumptions if you're talking about an actual gas? They may name the gas like carbon dioxide, so you have a real gas. So what flaws would there be in the assumptions if you're dealing with a real gas? That's what we have to try and deal with. And that's exactly what I'm going to go at with you now, so I want you to be aware of that. Now, I have put an asterisk, whether you can see that there or not now, on numbers 2 and 3. You are best equipped as a chemistry student to defend these by using 2 and 3. 1, 2, and 3 are fine, in fact, but we need to go through them that way. I'll go through them in sequence now again. If you were dealing with a real gas and we said they're in constant random motion, well, there's a limitation to that for regular gases, real gases, right? Because if you could imagine 2 gas particles flying through the air and they collide and then they go off again along their own paths. Is it reasonable for me to say to you that somewhere along there they became stationary for a moment before they went off again? So they're not in constant random motion. They're not in constant motion. They're moving nearly all the time, but they're not moving constantly. So that's a limitation to that assumption. Okay? The word constant there. When particles collide, you would say in the exam, they become stationary for an instant before they move off again. And indeed, that would apply as well to the particle striking the walls of the container. They would be stationary before they go. If you're traveling in that direction and you want to go back in that direction, you'll have to stop going that way in order to go that way. So there's an instant where you stopped. And that's basically that you do not have constant motion then. That okay? That's a limitation for real gases. The second one is even better. There are no attractive forces between molecules. Now, you have, way back there somewhere in the early part of your course, you have covered this particular section on intermolecular bonds. Okay, it is the bonds that are formed between molecules. And I would like to think that you would deal with that in some kind of way again. Go back and revise it before you go forward now. There are 3 intermolecular bonds. Let me recap on them briefly for you. If you happen to have a non-polar molecule, there'd be van der Waals forces. Okay, H2, Cl2, as it happens, CO2 are non-polar molecules. Now, I'm saying it to you. I have to get you to go back and revisit that if you're in doubt about that. Can you tell me whether a molecule is polar or non-polar? If you can, you've no problem here. So, because if you have non-polar molecules without a plus or a minus end to them, then the only intermolecular bonds are van der Waals forces, right? And the van der Waals forces would exist between them, and therefore there are attractive forces. If there were polar molecules, okay, whole load of molecules are polar, water would be one of them, okay? I don't need to go into them now, but water would be one, H2O. Water has a shape like that. You probably know this already. That's delta minus, that's delta plus, and a delta minus. The center of the minuses is there, and the center of the pluses is halfway along here. So there's a minus end and a plus end to the molecule, so it's a polar molecule. And in that particular case, you happen to get hydrogen bonding, okay? And there's other molecules where you will get dipole-dipole. There's HCl. That's delta plus and that's delta minus. How would you know that? You'd have to go back and look up their electronegativity values. And that one is much bigger than that one. Therefore, that's polar. If they are a polar molecule, it's either dipole-dipole forces as you get between them. That molecule and the second one would have delta plus and delta minus. There is the intermolecular bond. There is an attraction between the molecule. You're saying there are no attractive forces. Yes, there are. As a chemistry student, you have most information to defend that. You can't answer that now without revising, I'm saying it for the last time, intermolecular bonds. Go back to the end of chemical bonding and revise that, okay? So yes, there are, and you have reasons to believe that. Depending on which gas they name, you can tell them what intermolecular bond is involved. Is it van der Waals? Is it dipole-dipole forces, or is it hydrogen bonding? Now, that's a separate section. We'll leave it for the moment. Number 3, the gas molecules occupy no space. That's equivalent to me saying here with my little model on the board that the dots do not cover any of the board. And that that's not right. They cover hardly any of the board, but they do cover some of the board. And that idea is very important then, that they occupy space. And can I ask you please to be particularly careful with that, okay? If you are, there'll be no issue, right? That you're going to say, no matter how small a molecule is, it's going to occupy some space. And that's most important, that you can do that, all right? And that's ultimately what you want. So that's an easy one to describe, really. The analogy I often use to clarify this, can I repeat it again for you, is dust. That this room would be full of dust, and yet we can't see it. We don't know where it is. It doesn't seem to take up any space. Yet if you brought a vacuum cleaner in here and you were to suction all the dust up, you'd fill a bag with dust. So those particles must be somewhere in the air, if you know what I mean. They can be very small, but they'll still occupy some space. The perfect gas or the ideal gas would be telling you they occupy no space. But in reality, all gases take up some space, and we have to accept that. The other two now are a bit more challenging, 5 and 6, and I'll ask you to be careful with them, okay? Avoid them, please. If you have a choice, go for 1, 2, or 3, and I've told you already you're best equipped for number 2, okay? Number 4 there says, the collisions are perfectly elastic. An elastic collision is a collision where no energy is lost. In reality, there's no such thing. But you'd have to do a bit better than that, you understand. No such thing isn't just good enough. That's not an explanation. When particles collide, there's always some energy lost in the collision. Okay, and consequently, they're not perfectly elastic. It could be lost as mechanical energy as they knock each other out of shape, or it could be a sound energy or whatever, and two things collide. So all I can say to you is there's no such thing as a perfectly elastic collision for a real gas. Very important. And number 5 here, the kinetic energy of the molecules is proportional to the temperature. Yes, that's right. Generally, as you raise the temperature of a gas, the particles travel faster. I've told you that already. But the flaw here is proportional to. That's the flaw here. The suggestion would be that if you drew a graph of kinetic energy against temperature, that you'd have some kind of a straight line. That doesn't happen. If you increase the temperature, the potential energy, the kinetic energy, increases slightly, but not proportional to it. This would suggest if you double the temperature, you double the kinetic energy. No. So the flaw there is that, okay? There's a more complex explanation for that, which I won't deal with here now, but in fact the temperature is related to the inverse square of the velocity. Okay, will you just take it, please? But that's another day's work. You don't need that, and don't bother going there. But it's to say that if you double the temperature, you double the kinetic energy is not right. If you double the temperature, the particles will get a little bit faster. Yes. But the proportionality is the problem. Now, they are the 5 assumptions of the kinetic theory. It's important you know them. It's important that you realize that each and every one of them has a limitation when you're talking about real gases, okay? And it's very important that you're aware of that. There are limitations to these assumptions for real gases, so they may well name a gas for you now. The minute they name a gas, it's a real gas. These assumptions will hold for ideal gases. I'm going to get to the ideal gas concept in a moment. Now, they're likely to ask you the following question, and I'd ask you to be aware of it. Under what conditions of temperature and pressure does a real gas come closest to ideal behavior? Now, you have a study plan from me on gases, masses, and moles. And that's actually written in there in the list, okay? It's written in the list. I won't trouble you with it anymore. Low temperature, low pressure, and high temperature. Low pressure and high temperature. Okay, they're the two conditions. If you could get those conditions with real gases, you'd be close to an ideal gas, okay? And let me try and qualify that for you. That's one gas there. Here's a second gas here, okay? There's a gas at low pressure. Less collisions. Remember at the beginning now, all down here, the volume of a gas is the volume of its container. The temperature of a gas is the speed of the particles. And the pressure of a gas is the number of collisions. Now, won't there be less collisions here than here? If there was only a few particles inside the container, or if they had loads of space, is it fair to say that they would be practically moving all the time? That they'd be very far away from each other, so there'd hardly be any attractive forces between them? Is it fair to say there's so few particles they occupy no space? I hope you're getting that idea. So low pressure would mean you'd be close to ideal behavior. And high temperature is referring to the fact that these particles are traveling faster than the others. And if they're traveling faster, they'll have less effect on each other. Okay, in general terms, they'll be moving most of the time because they're moving so fast. Okay, and their attractive forces would be less effective when they're moving fast. Okay, less effect on each other, and occupying less space is something maybe not the easiest to deal with. Perfectly elastic collisions, you're getting closer to that when they're faster. Now, maybe some of you just need to realize you must know this. You must know that they're the conditions under which any real gas would be close to ideal behavior. Now, don't be deceived here now in the question. They could name any gas and just say to you, when would this gas be close to ideal behavior? It could be as simple as that. And you must know these two, low pressure and high temperature. Okay, remember, low pressure means there's less collisions, so there's less particles probably, or the container is very big, one or the other. And high temperature means, of course, that they're traveling much faster than the cold gas. And that would be very important to deal with that. That's very good. Now, the only other thing I need to deal with in this is, I'm going to put it up now, is the ideal gas concept. And we dealt with most of this already, but just the ideal gas concept, I hope you're not lost on this, that you didn't miss out on it, because it's very important that that unit is complete. Now, here we go. An ideal gas is a gas which obeys all the assumptions of the kinetic theory under all conditions of temperature and pressure. Now, I've already mentioned to you, I'm repeating now, an ideal gas doesn't exist. It's the perfect gas. It's the gas that all other gases aspire to. Okay, it's a concept more than anything else, but it's important. The ideal gas would behave like that, okay? It would obey all the assumptions of the kinetic theory. Remember, real gases do not obey all the assumptions of the kinetic theory. Okay, there are limitations when you have a real gas, and that's very important. To use this concept then, here we go. This is a constant for all gases, PV over T. I've made that earlier in a previous video, now you know that. If it's a real gas, then PV over T equals K. But if it's an ideal gas, PV over T equals a special value R, which is given on the front of your exam paper, 8.3 or 8.31 metric units. And therefore, 1 mole of ideal gas, PV over T equals R, so N moles would be equal to N times R, and you end up with this formula, which I have dealt with in detail with you already. PV equals nRT. Now, I'm going to finish this shortly now, because this is just a piece that was annexed from one of your videos, and I want to make sure it's not missing. Okay, that's called the ideal gas equation, and I'm going to ask you a question now. What is the precautionary note you must have with that? What is the heads up you need with this? Isn't it that the units must be metric? Yeah, will you remember please? R equals 8.3 metric units. They'll be given to you, okay? Don't worry about it, they'll be given to you, right? What are they? If you really want to mess around, solve for R and that and you'll get your values, okay? But don't worry. Because that's metric, everything there must be metric. And I'm finishing now with this again because there'll be serious consequences if we get it wrong. I'm reminding you, the pressure must be in pascals. The volume must be in meters cubed. Now, go back to the previous video, you'll see this. Okay, meters cubed. Can you convert centimeters cubed to meters cubed? You multiply by 10 to the power of 6, isn't that right? There's 1,000,000 centimeters cubed in a meter cubed, which you must go to meters cubed now. Remember a meter now, please. That's a meter. By a meter, by a meter. That'll be an awful lot of gas. Okay, so be aware of that, please. That must be that. That has got no units. That's metric. And this one, be careful, please, must be Kelvin. You usually get temperature readings in the lab in centigrade. And you must, of course, Celsius or centigrade, and you must convert them to absolute, okay, to the Kelvin value, which is, of course, going to be adding 273. Now, please, it would be a shame that you would slip up on the units here. And I'm reminding you, when would you use that formula? Anytime they give you the volume of a gas and they state its temperature and its pressure, you can very quickly calculate how many moles of that gas you have. Yeah, that's its primary function. PV over RT. You'll be given that, that, and that. They must be in metric, and you'll get moles here. Can I remind you, the mole is a very big quantity. Don't be surprised if that is actually quite a small number. Okay, now that was edited out of the previous video. Will you please make sure that you have that in the right context? Go back in the previous video if you're unsure of this. All right, good.